Hello everyone, my name is Caden Howlett. Welcome to the YouTube channel if you've never been before. I am a PhD student at the University of Arizona and I study geology, and that is going to be at least partly the topic of today's video. I want to start the video by reading a quote, or at least an adapted version of the original quote from a very famous scientist, Galileo. And this quote I have written down to my left here is, quote, "It is my opinion that the earth is very noble and admirable, and if it had continued an immense globe of crystal wherein nothing had ever changed, I should have esteemed it a wretched lump of no benefit to the universe." You might have to go re-listen to it, but the reason I find that so beautiful is because it's kind of a nod long before its discovery of the beauty of plate tectonics. Plate tectonics is the scientific theory that the Earth's lithosphere, or the crust and the uppermost mantle, actually moves around on the subsurface. Some people have referred to this as continental drift, such as Alfred Wegener, who first kind of came up with this idea that there are several rigid, or at least semi-rigid, tectonic plates that are mobile atop the asthenosphere and the underlying mantle. So what Galileo was saying is, like, if there weren't plate tectonics, it'd be a pretty boring place. Like, if things weren't as dynamic as they are because of plate tectonics and the associated stresses and resulting strains, what would we have to do, especially me and people like me who study tectonics. So with that little introduction, the purpose of this video is going to be a little bit in depth into a short paper, pretty basic writing though, called A Tectonic Manifesto, kind of a perspective article, not really in the data weeds or anything, but it's by Robert Stern, Taras Gurya, and Paul Tackley. This was new last year. And my vision here is to just go through this paper, kind of giving my reactions to some of the main points. The basic structure of the paper is, I should say the motivation and the structure associated with that is that as we get all excited about exoplanets and complicated relationships between things like climate and plate tectonics, and perhaps more interestingly, life and plate tectonics. Obviously, all three of those things are intertwined. We really want to have a good idea of what plate tectonics actually is. What is the definition of plate tectonics? How does it differ from tectonics? And what kinds of possible differences may we see in the behavior of the shells of exoplanets that have different characteristics, things such as temperature, not only surface temperature, but subsurface temperature, and the intensity of things like convection that in many cases dominate the scene in terms of mantle and lithosphere feedbacks. So we're going to go over to the computer here. I'm going to share my screen and we're just going to go through a short 3-page document here, and it's organized into a nice little list for us. Okay, so here we are. New publication from Robert Stern. He's been writing a lot of things that I find super interesting that have to do more with the philosophical side, synthesis side of tectonics and broad scale Earth processes. You can see the author list there. And I'm just going to read this abstract, and in fact I'm going to be doing a lot of reading here. This is my goal, and I really just want to highlight the things that I think are the most interesting from this list of concepts that they outline in the context of planetary behavior and plate tectonics on different types of solar system, I should say celestial bodies. So reading the abstract together, tectonics is the scientific discipline that studies the relationship between planetary convection and surface deformation and magmatism. In recent years, global tectonic regimes and planetary evolution have become foci of astronomical and planetological research, dealing in particular with potential habitability of planets orbiting other stars in our galaxy, known as exoplanets. This broadens the scientific impact of tectonics and makes it useful to outline a few guiding principles. For many, the term tectonics is synonymous with plate tectonics on Earth, and it should not be limited to only the planet we know best. Specifically, the concept should be generalized to encompass other rocky planets and moons in our solar system and exoplanets. And then, as I said, the article summarizes 15 general concepts about how different terrestrial in our solar system and exoplanet bodies are expected to behave. And so, skipping the first part of the introduction, we're just going to jump right into the list here. This video hopefully will be helpful to come back to. Particularly, I should highlight the fact that I will put the link to this publication in the bio so you can print it out for yourself, because I'm going to keep it in my back pocket for the rest of my career. Point 1. Tectonics encompasses magmatic processes, thermal and deformational history, and the evolution of the lithosphere of planets and moons, where the lithosphere, which for the Earth includes the crust and part of the upper mantle, as I said earlier, is the more rigid outer layer on top of less viscous ductile mantles, sometimes called the asthenosphere. Importantly, tectonics involves the entire lithosphere. This is interesting. It's becoming a lot more obvious from modern tectonics research that there are things going on in the subsurface of Earth, that is to say the base of the lithosphere and its interaction with the underlying mantle, and how it may be related to surface deformation. Things like delamination or dripping of the lowermost lithosphere into the mantle, and also things like at subduction zones where you have oceanic crust plunging into phase changes such as the 660 kilometer discontinuity, where you may have upper plate responses to what's going on in the mantle. So tectonics involves the lithosphere. They go on to say something interesting about how the article doesn't discuss ice tectonics. I was just talking with someone at a club fair for the College of Science at UA last week about ice tectonics on Enceladus, and that is one of the icy moons of Saturn. And it's just interesting that there are some similarities that can be drawn between the way that icy shells behave and the surface of Earth. So they just go to say that we're going to be talking a lot about convection and density contrasts on rocky planets, and so it doesn't apply to ice moons or ice planets for that matter. Cool. So point 2, important definitions. Lithosphere is the relatively cool, strong, and rigid outer part of a silicate planet or moon, brittle at the top and ductile at the base. So rocks at the surface of Earth, if you think about Nevada in the western USA, it is characterized by brittle deformation, basin and range normal faulting, where the deformation is literal cracking and fracturing of rocks that aren't hot enough to flow. And so this is just saying that, like, when you're thinking about tectonics and stress transfer in the Earth and the resulting strain, when things get hot, things will flow. Quartz and feldspar, typical minerals on continents, will begin to ductily deform, and you can get ductile deformation. So just some more definition type stuff, re-emphasizing that the lithosphere is where tectonics happens. Just even if a lot of this, it seems like a lot of information, keep in mind as we set the stage that we're talking about the shell of planets. On Earth, this can be scaled to the equivalent of an eggshell surrounding an egg, or another common example is an apple skin. So in reality, it's a real small portion of at least a planet at the current stage of evolution that Earth is. This is interesting because it first mentions something I found very interesting All silicate planets and moons, whether tectonically alive or dead, have lithospheres after their early magma ocean stages, if they had one. They had. We're going to talk more about tectonically dead planets. I think that this is really cool, and how you might even have celestial bodies that go back and forth between having no tectonics, that is dead, and having some form of tectonics. Excuse me. So wrapping up the definitions here, tectonics is thus the surface expression of a thermally evolving body, with that evolution taking place both by active convection and by conductive and volcanism-induced cooling. Tectonically active bodies can be identified from characteristics of their solid surfaces. That's basically what I do, and what my research group does is we study tectonics using the solid Earth behavior at the surface, reconstructing tectonic activity. This is intuitive and good to have in your back pocket. Active bodies show youthful surfaces with volcanic and deformation features such as faults and folds, whereas tectonically dead bodies show old surfaces dominated by impact craters. So we can start thinking about, let's look at the Earth, let's go to Western South America, and there's a massive Andean mountain chain with a fold and thrust belt, active volcanoes, tons of folding and faulting, especially when you get on the ground and see the rocks. Compare that to images from the Mars Reconnaissance Orbiter, or especially the Moon, where there's no evidence of tectonics that is disturbing the modern surface of those bodies, and that's why they have so many impact craters and stuff like that. I can't help but think of Jupiter's moon Io, which is under such extreme tidal forces from Jupiter that it's the most volcanically active body in the solar system, and it's just constant. It's super smooth when you see the beautiful images from NASA, because there's just constant volcanism. So you can already see outside of the article making connections between, okay, this is already thought-provoking, because you start to think about different qualitative characteristics of planetary bodies that give you insight into planetary behavior. We're going to come back to this figure here because it's important once we've learned a lot more stuff here. This is a cool point. With point 4, with time, most silicate bodies cool down, although some conceivably could heat up, depending on the ratio of surface heat loss to internal heat production. This, things like radioactive decay in the Earth is important for internal heat. And they go on to discuss this thing that I hadn't actually heard of called the Urey ratio, which I didn't look into this, I meant to, but I think it's Urey of the famous Miller-Urey experiment, which was the experiment that basically first showed and was popularized as showing an ability to turn inorganic materials into organic materials. And they use the famous, lightning strike as a possible, it's commonly cited as an example of how life could have started on our planet, given some sort of primordial soup, as Carl Sagan would say. So I digress a little bit. So the Urey ratio in this case has to do actually with the temperature, the internal heat of planetary bodies. When it's less than 1, the body will cool with time. When the Urey ratio is greater than 1, the body will warm. So right away, we can see in the next sentence, it's estimated that the Earth has a Urey ratio of about 0.3. This means, according to that definition, that it's cooling with time. And you need to look no farther than the moon to see that smaller celestial bodies cool faster, right? The moon was once entirely magma, as was the Earth, global magma oceans, and they actually differentiate and cool down pretty fast. And as they go on to say, that's related to the size of the body. So think about a huge cake versus a cupcake. Which one would cool faster just has to do with the internal heat present, basically. The reason this is important is because if you have a body that cools down really fast, plate tectonics as we know it, tectonics I should say, as we know it on Earth, is not going to be occurring because that internal heat and density contrasts between things like oceanic crust and continental crust is a key driver, are key drivers of plate tectonics on Earth as we know it. So there's a little bit more information here on the Urey ratio, and then they go on to say something that I find really interesting. A tectonically dead silicate body with a Urey ratio greater than 1 could conceivably become tectonically active. So that is, if the body is warming, you could take something, and I don't know if it's due to maybe increased tidal stresses, like I mentioned with Io, due to some sort of gravitational perturbation, you might reignite tectonics on an exoplanet or a planet in our solar system. So that's cool. Point 6, when you have a cooling planet, eventually the lithosphere will thick and strengthen to the point where tectonics stops tectonics. What a sad day that would be. Continued cooling can result in interior shrinkage manifested as reverse faulting, as we see on Mercury. Another thing I'll say right here, this is fascinating that we live in a solar system where we have things like Mercury and Venus and Earth and Mars, and then the associated moons, that is the terrestrial planets, because we see them at different stages of planetary evolution, in this case, in the context of tectonics. And so it's cool to compare and contrast, obviously. And that's what we'll do when we go back up to the figure I skimmed by. Cool. There's some stuff in here about convection that is relevant, risings and sinkings in the context of convection. That is you'll see in intro textbooks the kind of boiling pot of water analogy of these convecting cells as hot material rises and hits the base of the lithosphere and then goes back down as it cools. Continued cooling, excuse me. Risings and sinkings are dominated by the up and down movement of upwelling plumes, downwelling drips and drapes. So moving on to point 8, speaking of mantle convection as being a high energy, far from equilibrium system that is farthest from equilibrium in the region of the highest temperature gradient, that is the lithosphere. So a point at the end of this section that I think is interesting is the Earth is the only silicate body for which we have a record of how its tectonic style changed through time, and there is no consensus interpretation of its tectonic history. People are still seriously debating when real plate tectonics started on Earth. Some people think it was soon after, or I guess relatively soon after the creation of, or I should say differentiation, that is 3 billion years ago, and other groups are arguing that it didn't start until 1 billion years ago, for example. There's lots of cool studies on that I can direct you to if you're interested. Nevertheless, the tectonic style of an active silicate body will change with time as the convecting mantle slowly cools and the lithosphere thickens. I kind of breezed over that earlier, but hopefully it makes intuitive sense that you would get thickening and strengthening of a lithosphere that is cooling down, right? It's kind of cool. Point number 9, the tectonic style of an active silicate planet mostly mirrors convective behavior. The interaction between the convecting mantle underlying the lithosphere and the response of the lithosphere determines an active silicate body's tectonic style. We won't get wrapped up into that because I think we've talked about a fair amount of that. They go on to talk about mantle plumes. This is interesting. We were just talking to Dr. Esteban Gazelle from Cornell here at UA last week, who studies the Canary Islands and the volcanism associated with a hot spot or a mantle plume there. Mantle plumes are these things that typically are thought to come up from the core mantle boundary, or at least somewhere really deep in the mantle, and then interacts with the overlying lithosphere. Tectonically active silicate bodies beyond the magma ocean will have plumes, and the number of plumes can help distinguish between vigorous silicate bodies like the Earth and Venus, sluggish like Mars, and then dead bodies like the Moon. There doesn't appear to be any active volcanism or tectonics on the Moon. This is cool because I love this definition of plate tectonics. Point 11, based on the presence or absence of a global, connected, mobile mosaic of rigid plates separated by narrow, high-strain plate boundaries. They classify tectonics into the plate tectonics on modern Earth, which I kind of already beat to death, and single lid tectonics. That is what it sounds. On the Earth, we have these, I think people typically say 13 major plates, and then lots of smaller plates that are trapped up in complicated zones. And single lid is just that there's basically one plate, I guess, or a rigid single lid, I've heard it referred to. And they go on to break things up in the context of single lid tectonics into some details that we'll talk about in that figure up above. Volcanic heat pipe, squishy lid, sluggish single lid, and stagnant lid. And like I said, we have the terrestrial planets and moons in our solar system that all serve as examples of these. So how convenient for us. This is the definition I was actually thinking of. Sensu stricto, plate tectonics is a global tectonic system powered by subduction in which the lithosphere is divided into a global mosaic of strong plates which move on and sink into weaker ductile asthenosphere. And then they go on to talk about how we have seafloor spreading, subduction zones, where you spread and create new oceanic crust and then consume it underneath continents or other oceanic crust and lithosphere. And then we have transform faults where two plates are sliding past one another. So that's plate tectonics on Earth. It's that simple. In your intro class, they'll be like, here are the three types of plate boundaries: divergent, convergent, and transform. Remember that, everybody. If you're an undergrad, I bet you know that. Point 12, the tectonic behavior of an active silicate body is likely to change through time. For example, from one style of single lid, such as the volcanic heat pipe or the squishy or stagnant lid, to another form of single lid, or to plate tectonics as we know it, or the other way around. Transitions like this take a long time. Everything in tectonics, as far as I can tell, we're talking millions to tens to hundreds of millions to billions of years, that is. So think about that. Think about exoplanets that have Earth-like plate tectonics, and then they cool off. And then, like I said, maybe some sort of weird gravity thing happens where their stuff gets shifted around, or introduction of some foreign sort of external heat that melts the existing single lid, switches things back to an active mosaic of plates. Crazy thoughts. This gets a little more philosophical in point 13. Because of the nature of high energy, far from equilibrium emergent systems, the far future tectonic cycle of an active silicate body cannot be predicted in detail. So these are like, think about the sensitive dependence on initial conditions and an inability to determine what's going to happen to a planet in the long future. And our job as people studying tectonics on Earth is to try and understand, using the rock record and techniques, laboratory techniques, how the styles may have changed over time on Earth, and it's proving to be very difficult. So we start on Earth, and it's one reason that geology in general is so humbling and interesting is because it's like we have all these grand ideas, but it's like, damn, we really need to figure out if we can't figure out what's going on Earth, how are we going to speculate and intelligently do science on other bodies, Moving down the list a little bit, concepts and guidelines articulated above will surely need modification as we learn more about exoplanets. This part I love. Here are a few examples. When I read that and then the subsequent list, I was like, yeah, here are a few examples that are great. And it's so fun to think about all the other possibilities out there in galaxies that have so many billions and trillions of exoplanets. I just think of planets that are like, whose entire surface is moss or something crazy, like who knows what's out there. Certainly ice and rock, a lot of it. So their examples are extremely high surface temperatures, like magma worlds. You can't have tectonics if it's just a global magma ocean. Another cool thing is point B, surface temperatures over 1,000 Kelvin, that is ductily deforming and perhaps, like full melting rocks at the surface. Whereas like we have a geothermal gradient where things start to behave ductily in the lower lithosphere, as previously mentioned. Like they raise the question, is there tectonics on a planet that is ductile at the surface? Who knows? Part C, this is a cool one. Tidally locked exoplanets. They can be hot, even molten on one side, but cold on the other, so that each hemisphere could have a different tectonic style. I don't know about that one. I'd have to think about it, but it's insane to think about. Think about Earth-type plate tectonics on one side and then just like cratered moonscape on the other side because of tidal forces. Pretty cool. And then the last one is extremely large. I love thinking of this too. Enormous exoplanets. They must exist out there. It makes me want to read about some of the size estimates that that NASA and other scientists have right now. In large, actively convecting silicate exoplanets, the asthenosphere can exist at an even higher pressure than the neutral buoyancy depth of partial melt, so that magma cannot rise to make crust. Crazy. Finally, global tectonic style has a strong effect on planetary degassing, ingassing, atmospheric composition, and climate, therefore the emergence of life and evolution. In planetary history, major changes in global tectonics may also be associated with major changes in atmosphere, climate, landscape, and life. Hopefully goes without saying, the linked nature of tectonics, climate, and the origin and evolution of life cannot be denied. Very cool. The last thing they say is that these things will have to be modified as we learn more, and what else do we have to do that is a better use of our time, my friends, than trying to figure out the complexities of the universe. And so I come back up to figure 1 here. This might make a little bit more sense if you stayed with me this long. I know I read a lot there, and that was my intention, and hopefully it mostly inspires you to go read it for yourself, because I think that would cement it. But this is a cool comparison of bodies that we know about, most importantly that we've mentioned, things like Io, heat pipe, where there's so much convection and partial melt because of tidal forces that it's just constant volcanoes at the surface with no clear plate tectonics. Venus is believed to have a convecting mantle as well, and maybe short-lived tectonics. They refer to that as a squishy lid. Kind of funny. Plate tectonics on Earth, so beautiful. Those 3 types of margins that we have, and shown here, I suppose, is a subduction zone with subducting lithosphere going on and convection in the mantle. Maybe some plumes on Mars and some really sluggish tectonic activity going on where you might have dripping as well, and earthquakes and volcanism associated with that, but obviously not a lot of evidence of active volcanism or plate tectonics of any kind on Mars. And then the moon, she cold, you know? Thing cools off fast, stagnant lid, no convection, heavily cratered, nothing going on. So it's dependent on the size of the body. And I hope that this little overview has given you all something to think about, different styles of convection, the behavior of planets in terms of their thermal state and the effect that that has on plate tectonics. It's really important whether or not something is hot or cold to have anything resembling what we have on Earth with subduction and volcanism. And importantly to me, the reason I was inspired to make this is because of its relation to exoplanets and just using our creativity and even just leisurely time to think about the types of exoplanets that might exist and what effect that might have on tectonics, which, like I said, is intimately linked to the evolution of Earth. So I think that tectonics is one of the most important things in the universe, and I mean that, and that makes me feel good to say because, you know, it's what I do. Maybe I'm just hyping myself up, but I'm trying to hype everyone up, you know? It's a beautiful pursuit. And let me know if you found something particularly interesting, or if you, certainly there are people out there who are experts on this who could leave me some feedback and some papers to dive in a little bit more. My expertise is very much on Earth style, you know, of tectonics, but super fun to talk about. Shout out to Robert Stern and Urey and the whole author list here, Paul Tackley. You guys have been doing a lot of cool stuff that's inspiring me. So with that, I'll see you guys in the next video. Keep learning about space, and perhaps most importantly, Earth. Peace out, everyone. Thanks for watching.